Here we will see the solar and wind energy conversion system. And in this one, first I will see the introduction to the solar energy system. Now let us see photovoltaic cell. Introduction to photovoltaic cell. The photovoltaic cell is a semiconductor device that converts the light energy into electrical energy. Therefore, the light energy is being converted into electrical energy by photovoltaic cell. The voltage is induced by the PV cell that depends upon the intensity of light incident on it. Therefore, the voltage that is being developed is proportional to that depends upon the light energy that is falling on this PN junction. The name of photovoltaic is because of their voltage producing capability from the light. Since the energy, light energy is converted into the electrical energy, that is photon. The light energy means photons. Photon energy, that light is being converted. That is why it is called photovoltaic. The electrons of the semiconductor materials are joined together by the covalent bond. As you know that when a semiconductor material, outer layer of the electrons are being connected by the covalent bond. As the light energy is falling on this, what happens is that when the photon incident on the semiconductor material, these electrons are being energized and they are start emitting. That starts emit that electrons. Or the covalent bond is being broken and the electron starts emitting. And these energized electrons are known as photoelectrons, because by falling the photons energy or light energy, the electrons are being emitted. That's called photoelectrons. And the phenomena of emission of the electrons is known as photoelectric effect. That effect is called photoelectric. And the working of photovoltaic cell depends upon that is called photoelectric effect. Continuing photovoltaic cell introduction, that consists of a PN junction, and in that one the photons, the light energy is falling on the junction, and here electrons will be emitted. Then electrons will be moving from the N type to the P type material. For electron flow is in this direction. As you know that the current flow will be opposite to electron flow. Therefore, there will be a current in this direction. Therefore, the electrons flow from the N side contact through the load and back to the P side, where they recombine. The electron that is coming here, that recombines in the P-type holes, and the holes in the P-type material, and the conventional current is always opposite to the electron flow. Therefore, current will be flowing through the load. Coming to the construction of solar cell, a solar cell is basically a junction diode, although its construction is a little bit different from the conventional PN junction diode. A very thin layer of N-type is grown on relatively thicker P-type material, and then a few finer, very small electrodes are provided or that fixed on the top of the N-type as well as P-type material. Therefore, this is the picture of a PN junction and PN diode as such, and from the N-type material electrode is taken and another electrode is taken from the P-type material. Coming to the solar cell, and as you know that one here is in a solar cell, a PN junction, that it can produce a voltage, or that junction voltage will be equal to 0.5 volt only. Single solar cell voltage will become 0.5 volt only. And its current for a solar cell, it can, for example, it is 4.44 amperes it can drive or it can supply, and voltage equal to 0.5 volt. Therefore, the power is product of this current and voltage, which is equal to 2.22 watts. For a single cell can produce a power of 2.22 watts. But whenever you want to have a higher power rating, what is the method? How can we generate higher wattage using a single solar cell? It's not possible by a single solar cell. Then in that case, in order to increase the voltage rating, these cells are to be connected in series, and in order to increase the current rating, these cells are to be connected, or these series cells are to be connected into parallel. Therefore, in order to get a higher power, many cells are connected together in series and parallel in the solar PV module. That's what's called as PV module. We call it as PV module. In PV modules, there will be number of solar cells. They are connected in series, and such series cells are connected in parallel. Continuing as the working of photovoltaic cell, PV cell, as we have seen this already, that we are figure we have seen. Considering the figure below shown, PV cell mode of silicon and the resistive load is connected across this. So for PN junction and solar light energy is falling here, and in this junction a load is connected between N-type and P-type material. For the PV cell consists of P and N-type layer of semiconductor material, P and N layer of semiconductor material. These layers are joined together to form the PN junction. For a PN junction is being formed, and the junction is the interface between P-type and N-type material. And when the light falls on this junction, falls on the junction, the electron starts moving from one region to the another. For electrons will be moving from the N-type material to this direction, and for the current will be in the opposite direction. Here, continuing the working of photovoltaic cell, it is important to know that all impinging photons are not releases that won't release electrons from the atoms, because atoms to become charge carriers. A photon with short enough wavelength and enough high energy can cause an electron in the photovoltaic material to break and free the electrons. Or certain frequency wavelength, only certain wavelength of high electrical energy can emit the electrons. For all this, the impinging photons cannot produce the electrons. Generally, the term solar cell is reserved for the device intended specially to capture the solar energy from the sunlight, that is solar cell. But in commonly, while in terms of photovoltaic cell is used when the source is of unspecified. If the source is not specified, we call photovoltaic cell. But if the source is solar energy, then we call it as solar cell. Next, we have to see the IV characteristics of PV cell. Before that one, let us see the diode IV characteristics. As you know, already you have studied that one. In a diode PN junction, what is the relation, or how current and voltage, current through the diode and voltage across the diode is related. Now, as you will see that one, this is the IV characteristics of a diode, in which this is the forward bias one and this is the reverse bias region. And the diode current in forward bias case, as you know that one, it is equal to reverse saturation current I0 into e raised to q into VD divided by k into t minus 1, where the ID is the diode current in the direction of the arrow. That is the diode current in this direction. That is the ID. That is in amperes. And VD is the voltage across. That this VD means the voltage across the diode terminals from the P side to the N side. That is from this to this. What is the voltage drop? And I naught is the reverse saturation current in amperes. And Q is the electron charge, which is equal to 1.602 into 10 raised to minus 19 coulombs. And here K is the Boltzmann's constant, which is equal to 1.381 into 10 to the power of minus 23 joules per degree Kelvin. And T is the junction temperature in degree Kelvin. Therefore, this is the equation relating the current through the diode and voltage across the diode in the forward bias case. So this is the diode current equation. And at 25 degrees centigrade, you can substitute the T for that one. In that case, as well as you can substitute for the Q as well as K, etc. You can substitute in this equation, and you will be getting the diode current in this, when it's a forward bias case, ID is given by reverse saturation I0 into e to the power of 38.9 into VD diode drop minus 1 at 25 degree centigrade. If you look into the ideal equivalent circuit of a photovoltaic cell here, this is a photovoltaic cell, that is a sun solar energy is falling in that one. Therefore, that is acting as a current source. It is actually it's called short circuit current, actually ISC. It is actually working as a current source, and the equivalent circuit of PV means a current source in parallel with a diode. So this is the equivalent circuit of a photovoltaic cell. In the ideal case I am telling, this is the ISC and this is the diode. So this is the PV ideal characteristics, ideal equivalent circuit of course, and the load is connected across this one. This is the load connected that one. Therefore, in this case, what is the current through the load? I is given by what is the short circuit current ISC from when light is falling. What is the short circuit current ISC? That minus what is the diode current ID. That is the current through the load. And already ID we have derived, which is equal to I naught into e raised to QVT divided by KT minus 1. Therefore, the current through the load in the case of a solar cell here, it is given by the short circuit current ISC minus I naught into e raised to QVT Q, that is voltage across the diode, divided by K into T minus 1. Now coming to that, what is the short circuit current and what is open circuit current? Find it. Short circuit current means that when PV cell is being shorted, that is when this is being shorted, when the load is made 0 here like that one. When this is shorted here, PV cell is being shorted here, what is the current? That is called short circuit current, ISC. That's called ISC. And similarly, when this is being open circuited, what is the voltage across that one? That is called voltage, open circuit voltage, VOC. Therefore, VOC can be obtained by open circuiting this one load, and short circuiting by this one we can get what is the short circuit current. We have already seen the ideal characteristics of a diode as such. Now coming to a solar cell, what is the current voltage characteristic? As you know, so that's already seen the current that is through the load or that's supplied by the, of course, the photovoltaic cell is equal to the short circuit current minus reverse saturation current to E raised to Q into V voltage across the diode divided by K into T minus 1. This is the equation relating the current that is supplied by the PV cell as well as the voltage across the PV cell of IB characteristics. Therefore, it is interesting to note that the second term in the above equation is just diode equation. Therefore, this second term is the diode equation with a negative sign. Therefore, here there is a negative sign. It's a diode equation with a negative sign. Therefore, that means that the plot of the above equation is just ISC, that is this ISC and short circuit current added to the diode characteristics in the first quadrant, that is turned upside. When it is being turned upside one, what is that is being added with the ISC, that is the characteristics of the IV. Therefore, that is current through the current supplied by this one is given by, for the photovoltaic current voltage relation for a dark case, that is when there is no sunlight, as you know that ISC will become 0. Therefore, the corresponding IV characteristics will be this one, since there is no short circuit current when in the dark case. And when light is falling, when it is being illuminated, sudden short circuit current will be happening that one. Therefore, that is being illuminated. The dark is just the diode curve turned upside down. Therefore, this is a short circuit current. We are adding this one, this diode characteristics that is added with this one. Then you will be getting this one. Therefore, this is the characteristics, or this is the IV characteristics of a solar cell as such. This is called short circuit current. When it is shorted, what is the current it can supply? And this is called open circuit voltage. When it is open circuited, what is the voltage? Therefore, this is the IV characteristics of a photovoltaic cell. Continuing the solar cell IV characteristics, as already explained, the current that can be supplied by a PV cell is given by short circuit current minus diode current, that is I naught into e raised to QVD, or actually it is voltage across the diode QV divided by KT minus 1. Therefore, this is the equation, and that is this one, that is this is the relation IV. For when the load from the PV cells are left open, that's all, from the loads are open means open circuit voltage or current is equal to 0, and we can solve the equation. That is, if in order to solve for VOC, what we have to means that from this equation, if you make the current equal to 0, then here corresponding voltage is called open circuit voltage VOC. If you substitute in this one, you will be getting equation which is equal to K into T. From this equation, K into T divided by Q into natural logarithm of short circuit current divided by reverse saturation current plus 1. Therefore, this is the equation for the open circuit voltage. So, in order to get the open circuit voltage, we are making I equal to 0 and we are calculating what is the VOC. Therefore, this is the open circuit voltage, and at 25 degrees centigrade. If you substitute T equal to 25 degrees centigrade, you know what is the value of the K and what is the value of Q. Substituting that one, you will be getting it is equal to ISC minus I naught into e raised to 38.9 into V minus 1. Therefore, this is the equation relating the current and voltage of a photovoltaic cell. Now, come again, open circuit voltage is given by VOC is from this equation. VOC is given by If you substitute that one, substituting this KT and this one KT 0.0257, actually ISC do. Therefore, short circuit current ISC is directly proportional to the solar insolation. As solar insolation increases, short circuit current increases, which means that we can now quite easily plot the sets of PV current voltage, that is PV current voltage curves for a varying sunlight. As the sunlight varies, the short circuit current changes, and then in each case you can plot what is the IV characteristics, the current versus voltage characteristics of the solar cell. Just like this is for a particular radiation. Now if insolation is increased, it will be above you will be getting, and again that goes like this one. Therefore, that is like that one you can sort or get IV characteristics of solar cell. What we have already discussed is an ideal PV cell equivalent circuit, but in practical case, apart from this, here there will be a series resistance and shunt resistance. So for equivalent circuit of a PV cell, in practical case, there will be a series resistance as well as a shunt resistance that is coming here. Therefore, this is the equivalent circuit. In that case, the current that can be out from the photovoltaic one is given by the total current that can be supplied, that in this case is marked as a I phase, minus the diode current, minus this shunt current ISH. Therefore, that is the current through this can be supplied. Therefore, the voltage current characteristic curve of a PN junction diode is given by the following Shockley equation. As you know that ID equal to, in this equation, ID, that diode current ID is given by I e raised to QVD divided by KT minus 1. Therefore, this is the ideal, so not ideal, practical equivalent circuit of a PV cell.